Hello everybody. In the Programming Language Concepts course, in this video I am going to continue and hopefully finish Chapter 6, the Chapter 6 lecture. Chapter 6, if you remember, is part of the 6, 7, and 8 PowerPoint slide presentation. Take a look at the last video if you'd like some more information on where to get the PowerPoint itself. It is on the website, the class website. And so this is Chapter 6. It's on data types. We stopped on records, so we will be doing records, unions, set types, and pointer types in this video. I've already covered the primitive types, user-defined types, and array types. So let me go up to the records where we left off last time. And so this is part 2 of Chapter 6. So if you have not read or looked at part 1, go back and look at part 1 before looking at part 2. So the record. What is the record? We all know in C, actually it is supported in C++, but it's really a C concept. The record is the struct. I'm saying struct, S-T-R-U-C-T, struct. So the record is contains heterogeneous aggregates of data elements in which the individual elements are identified by names. So you could mix and match data in a struct. So you could have a float, you could have a double, you could have a string, you can have a different, or what they call heterogeneous, different types of data all in the same structure, where an array is the same type. So that was first introduced in COBOL back in the 60s. And it is in almost all languages. It is not supported in Java because Java is an object-oriented language and struct is not, and the record type is not an object-oriented concept. It is still in C++ because it got carried over from C. But I want to say that C is probably the last language that has a record in it. So some design considerations. Remember when it says issues that these are not bad things. These are issues. It's not a negative word. It's a positive word. It means considerations or things to think about. So some design considerations that are specific towards records is what is the form of references? So this means how are we referencing the elements inside of the struct? Are we using a dot notation, which is what we're using in C? Are we using index values? Are we using names? So primarily the C struct turned into the C++ class. So if you've never used a struct before in C, but you have used a class, then you know what the reference form is. It's the dot notation. So you can put in the name of the particular object or the name of the struct, dot, and then the name of the variable that's inside of it. And then another consideration is what unit of operations are defined or supported. Meaning, can you add two structs together? Can you compare two structs to see if one is equal to the other, or is one larger than or greater than another? So what kind of operations are valid for the struct is one of the considerations. Now in the record field references in COBOL, which is a very old language, it used the field name. So you had field name 1, a field name 2, field name 3. Others use the dot notation. So instead of using field name, C decided to go with what's called the dot notation, using a dot to reference elements inside of the record. So fully qualified references must include all of the record names. I'm not going to get into these other COBOL and PL references because they don't really exist anymore. I mean, they're not really used in the mainstream languages. And we don't use the with clause anymore either. But in C, C++, we have the individual fields of the structs are accessed either by the dot or by the arrow. If the arrow is used, if it is a pointer, the dot is used for non-pointer data. So just in case it's been a while since you've seen a struct in C or C++, here's an example. The struct is at the top of the code here. This is the struct student. And it has an integer social security number and a character grade. And in the program under the void main, we have two. We have student John, and we have a pointer to John. So we have two variables, a pointer variable and a student they're both student data types, but one's a pointer, one's not a pointer. And then for John.grade is equal to A, we use the dot for the non-pointer, and then we use the arrow for the pointer. So it's just showing you what the dot and what the arrow look like to set the grade. The grade is inside of the struct. So hopefully you've seen those before. So in terms of the record operations, when it comes to assignment, C allows, and I'm going to skip the Ada and the Pascal because you're not going to probably ever need to know any of that, and you don't need to know it for the purposes of this course. If you know how it works in C or Java, you're pretty up to date with it. So C allows assignment expressions if the types are identical. So if I have two structs, two variables, they're both using the data type struct. One of them's A, one of them's B. I can assign A to equal B as long as they're of the same struct. And for example, the struct student, if I had student A and student B, I can say that student A is equal to student B. That would be an assignment expression. And I'm talking about number one here under assignment expression. I could assign A to B in C if they're both student structs, as that particular example holds true. For the initialization component, you can't really initialize a struct when you create an instance of the struct like you can a class object in C++. C never had really those features. In Ada, it was allowed in Ada using aggregate constants, but it wasn't really allowed in C. You could create the variable and then you add something to it. So it's just kind of like regular variables in C, where we have an integer I, and you can say integer I is equal to 5, but you have to do a declaration and initialization in two separate or one step together, but it's separated out. In the form of the initialization for a struct, you have to go, student name, let's say the student struct was Bob or John, john.name, john.age, john.gpa. When it comes to the comparisons in bullet point number 3 here in Ada, you had the equals or the and or equals. One operand can be an aggregate constant. You can't really compare structs too much in C++. In C, actually, it's not allowed at all. I shouldn't say too much. It's not allowed. You can't really say if one struct is smaller than or equal to another struct. You can say if they are both the same identical struct data types, you can see if they're equal, but you can't basically see anything else associated with it. It's kind of like pointers. Two pointers will never be equal because the memory addresses are never equal. And a struct in C is considered a memory address. So unless you're using the same memory address, the same struct type, it's going to be really difficult to do a comparison with it. So it's very limited. So move corresponding, so we have nothing associated with that in C. But in COBOL, it moves all fields in the source record to fields with the same name in the destination record if you copied one to another. But we don't get that. You can't really copy one struct to another struct unless it's the same one and you're doing an assignment. So rule of thumb in C or C++, if you're going to use the struct, they need to be the same struct. So the same, even though not all structs are created equally, you can't just mix and match. It has to be the same struct that was created. So comparing records and arrays, if we were to compare and contrast the concept of the struct versus the array, access to the array elements is slower than access to struct elements or struct fields because the subscripts are dynamic and the field names are static. So that is true. So it's easier, believe it or not, to get at array indexes by their index values, 0, 1, 2, 3, etc. However, it's going to be slower because you have to go and traverse through 0, 1, 2, 3 to find what you're looking for. It's a linear search. You start with 0 and you search each one of the items to find what it is you're looking for. With a struct, you just give it a name. I just want John. I want John's first name. I want John's last name. So you go directly to it. It's a hashed kind of structure with an index that is associated with keywords or keys, and then you get the corresponding data that's associated with it. So you kind of have like a key value lookup that's hashed, very similar to the dictionary in Python. So the retrieving the elements out of a struct is faster than retrieving elements out of an array. But when it comes to efficiencies and data structures and algorithms, when you look at the efficiency of an array, it always ranks on the bottom of the list when it comes to being efficient, because it is a linear search speed. And you have to do a linear search in order to find anything in it. So structs are a little bit more efficient that way. Dynamic structs could be used with record field access, but it would disallow type checking, and it would be much slower. A dynamic struct would be one that you'd have like in, for example, in JavaScript. In JavaScript, you can actually create a dynamic struct or a dynamic class object. Actually, not a class, it's just an object. You just pull it out of thin air and pretend it exists, and you start using a dot notation with it, and you just start adding components to it. Take a look at JavaScript one of these days and take a look at the way that objects are implemented, and you'll go, wow, that's weird, because there's no class template to it. If there's no class template, then it's dynamic. So if you're not going to create a class and then make instances of the object using that class, then you're doing it dynamically. And so to do it dynamically is you just kind of pull it up while the program is running, and it just kind of creates itself without any predefinition or any preset order to it. So in the implementation of the record type, remembering we take off our programmer's hat, we're putting on our programming language or our programming compiler. We're going to create a compiler, and the compiler, we have to define how a struct is actually going to be loaded in memory. Here's an example of how we could do it. And so we could do it contiguously, as this picture shows, with record name, type, offset, name, type, offset, etc. and so forth. The types of the records are stored in adjacent memory locations. The offsets are relative to the beginning of the fields. Basically, you're looking at sequential. This is not index values like 0, 1, 2, 3. Instead, it's the name constant of the field. But you still have field, stored sequentially, very similar to how you would implement the data storage for an array. So it's very similar. Some languages, like C, actually support the union as well as the struct. The union is considered a record type. The union is a type whose variables are allowed to store different types and different values during the execution. The only thing different between a struct and a union in the C language, or C++, is that the union only stores one piece of data at a time, where the struct can hold multiple pieces of data. So they said that the union was a lightweight struct, and it was kind of it freed up the memory where you didn't have to actually allocate memory for all of the different possible values that you could store for this particular piece of data, because you're only going to store one at a time. So it was more efficient. So some design considerations for unions is what kind of type checking, if any, must be done. So if I had, for example, a union, and in the union I could store an integer, float, a double, let's just say, or a character, how am I going to type check that? Type checking becomes a challenge, because how am I going to tell what it's supposed to be? If I have a union and it's going to be called weight, and I'm storing 12.5 in it, and I have another union and it's also type weight, and it's weight 2, and that one's storing 12. So I have a mixed number. I have a float or a double, and I have an integer, and I want to take this union and add it to that union. How am I going to check to see if the types are compatible when I can store anything I want, as long as it's defined? Whoops. Little screen there coming up. We don't want to do Catalina right now. So what kind of type checking, if any, is going to be done? That's an important consideration. Should unions be integrated with records, or should they be a separate data type in themselves? In some languages, there's just the struct. That would be Pascal, actually. In C++ and C, they decided, let's do a union and let's do a struct. But really, there's no advantage of they're the same thing. There's got two different names. The only advantage you have using the union is that it's a little bit more conservative on memory. It's not going to take up as much memory. So, some examples of unions and implementations in older languages from Fortran. They were equivalent, as I just mentioned. So in C and C++, the constant union is used. Well, it's actually the struct. So it's called union. And there was for a while they used to call them free unions because they freed up memory that wasn't being used for the other variables. So they were a little bit more memory conservative. You don't have to know about the Algor implementation of it. Back in the day, structs or records and unions were kind of popular, but this was procedural programming prior to object orientation. Objects have so many more features these days that the concept of object orientation is sort of taken over the record type in general. People would rather use an object than a record type because they just have more features to them. So don't worry about the Algor 64 stuff. Or don't worry about looking at page 231 of the book either, or any of the other union-related data there. Oops, what's wrong? So there we go. All right. So after the unions, we look at sets. So a set is sort of like a list, but the set only contains one of each type, just like the set you see in data structures. So a set is a type whose variable can store unordered collections, so it's not ordered, and they are distinct values for some ordinal type called the base type. So you could have a set of integers, you could have a set of doubles, a set of floats. Python supports the set. Java supports the set in the Java utils libraries. C, C++ never supported a set. You'd actually have to make one yourself. So some design considerations, unless you used template libraries. Now, when I say it doesn't support, I mean like the base language didn't support it. Microsoft Visual C++ supports it with the template libraries, but it's an add-on, not part of the base library, not part of the base library sets. So some design issues. What is the maximum number of elements in any set base type? Well, how big can the sets be? Which is an interesting question. So there's no index on them. There's no order to it. We do have to keep unique values to it, but are we going to put a size limitation on it? Kind of like arrays. You know, is it going to be static or dynamically sized? Is there going to be a limit on the number of elements that can go inside of it? So some examples of how it has been implemented in Pascal, where C, you know, the template libraries actually follow the Pascal. So does Java, by the way, and so does Python. There was no maximum size in the language definition. They were not portable. There was poor writability if the maximum is too small. Yeah, there would be poor, not portable and poor. Yeah, there would be writability issues because you wouldn't be able to, the set would be filled up. So sets are sort of dangerous in that you could allocate a lot of memory, have a really huge set, just like you can create a huge array, and it could have a negative effect on the performance of the program. But if you don't do that, then you might end up with the limitations put constraints on the programmer in terms of what you can accomplish with it. It kind of limits the writability of it. So. Operations on the set. Most operations are supported. We've got the union, the intercept, the intersection. The difference, is this set a part of this set? Is it less than this set? Are all the elements in here larger than the elements in that set over there? So Java includes a class for set operations, as I mentioned before. It is in the utils. Python also contains a set library, and so does C++ if you use the template libraries. So in the evaluation of the set, if a language does not have sets, then they must be simulated somehow, either the enumeration type or with arrays. Yeah, just like you can use an enumeration to actually implement a Boolean, you can use an enumeration to implement a set. That works as well. You could actually use an array as well. You just ignore the order. So the indexes don't mean anything, and you have to implement your own manual check to see if there's duplicates in the array, because the array is not going to the array is not going to check for duplicates on its own. So an array might be more flexible than sets, but has much slower operations because again, in an array, you have a linear search going through indexes. And so in a set, you could have a hashing function, and that hashing function could be used for a faster lookup. So it's kind of like in Python when you have the set, which could be similar to and the dictionary actually both work the same way compared to the list. The list has got a linear search pattern to it. Both the dictionary and the set, they have a hash index on them, or a hashing function associated with them. So when you look up items in these particular data structures, you're not going and looking at every single item. You're going to some sort of a hashing function, and you're using it for a quicker lookup. So they're optimized for faster lookup. So you really want a language, if you're going to use a set, you really want a language that supports the set as a data type and provides some sort of a lookup function for it. So in terms of the implementation, it's usually stored as a bit string, used logical operations for the set. So set operations are used. And then it's kind of like, the greater than, less than, is this part of this one, is that one part of that one. So the operations that are configured for the set are important, as well as the organization of how the data members of the set are actually stored in memory. So pointers. This is everybody's favorite topic from the nobody likes pointers for some reason. You get them in C and C++. You use pointers all the time in Java, but you never write one. You have pointers in Python, but you never write one either. So it's really the C and C++ language that really use the pointer concept. So a pointer is sort of like an alias. It's a type whose range of values consists of memory addresses, and it's storing the memory address of another variable. So we have a nil or null. That's usually a special data type that's supported in the language, where you can set a pointer to equal to null when it's not pointing to anything valid. So, or it's not pointing to a reference object. In C or C++, the value 0 is used for nil, and the programmer has to set it themselves. So if you've ever programmed with pointers in C or C++, you've run into possibly a dangling pointer, where you've got a pointer that's not pointing to anything, and it's not set to null, and you don't know that it's not pointing to anything valid, which makes it a dangling pointer. Or you can get memory leaks, and you can get all sorts of different problems that come out of pointers, because pointers are not the most reliable thing to program with in the C or C++ language. Some uses of the pointer: you have your address flexibility, you have indirect addressing, where you're able to get at something through another means rather than through the variable. So if I have a pointer, I can indirectly access the memory and the data that's stored for a particular variable or for a particular concept indirectly through the pointer. It also allows for dynamic storage management, or access to the heap memory of the process space. So the dynamic storage management is also an important feature of the pointer. So, some design issues or design considerations associated with pointers. We might ask the question, what is the scope and the lifetime of the pointer variable? When we create a pointer variable, does it ever go away? That's a good question. The pointer scope and lifetime of pointer variables in the C and C++ language are the same as regular variables. If I'm in main and I define a pointer and I go to a function, I have to redefine a new pointer if I want to use it or pass the information into it. The scope is local, and the lifetime of it exists while we're in main. If we go back to main, we can get our pointer back. When we go to a function, let's say, and we open up a function and we run a function call, we might define a pointer in the function. When the function goes away, well, then so does the pointer. So it's local scope for the most part, and hangs around for the life of the function for which we're running. What's the lifetime of the heap-dynamic variables? Now that's an interesting question. In the C and C++ language, heap-dynamic variables had a history to them, and they had an unlimited lifetime. They did not have a local scope, and they did not have local lifetime, which meant if we open up a function and we allocate something to the heap and we close the function, well, unfortunately, the heap is still allocated. And so that's why we have the copy constructor and the deconstructor in C++, is because the objects write to heap all the time. And if we write something to the heap and then the object goes away, we need a destructor to remove the object's allocated memory off the heap. Otherwise, we're going to end up with a memory leak because we're going to run out of memory because we've allocated, and we haven't deallocated anything. So there's built-in functionality in the C++ object to control the deallocation of the memory when the object goes out of scope. Because the lifetime of the heap-dynamic variable is unlimited. It exceeds way past the lifetime of the variable and the pointer reference itself. So I'm talking about number 2 here. In C and C++, that lifetime is forever. Until the program ends. In other languages, it isn't. But that's what it's asking about, the heap-dynamic variables. What is the lifetime and what should it be? And that's something, if you're developing a new language, you'd have to figure out for yourself, what should the lifetime be of the heap-dynamic variables? Also, number 3, are pointers restricted to pointing to a particular type? Now, that was an interesting part of C++ and C. Pointers are typed. So if I want to point to an int, I have to make a pointer int reference of the int data type. So I have to make a reference of the same data type as the memory I want to point to. In other languages, I don't have to do that. In Objective-C, as an example, in that language, there's a pointer type. It's called ID, which is a generic type. So you can make an ID for an object and just have it point to anything. It doesn't matter what data type the ID is actually pointing to. It can point to anything you want it to point to. In other languages, Java, you can do a reference. So as long as you create a reference of a data type that's in the hierarchy of the object, you can have that reference point to any other reference. So for example, if I had an object that was a human, and on top of a human, I had an employee, and on top of employee, I had a janitor, and on top of employee, I also had a teacher. I can make a reference employee and reference both the janitor and the teacher because they're both parts of the same hierarchy. They all come from employee. And so as long as I have that commonality in there, then I can create an employee reference and reference it to a teacher or reference it to a janitor or something. So, but that's what it's talking about. In terms of number 3, it's, are the pointers restricted to pointing to a particular type, or can you just point it to anything? Most static languages have the pointers only pointing to a particular type. So are pointers used for dynamic storage management, indirect addressing, or for both? In Python, they're used for both. C, C++, they're primarily used for indirect addressing. Java, they're used for both. Dynamic storage management means that the memory that's being allocated is on a heap. It's not allocated from a stack entry. And that memory is being managed through pointers or references, which is how Java and Python actually work. C++ does a lot of static allocation. So it's a static allocation technique where you've got a lot of C static variables that are stored on a static area. They're not stored in the heap. So pointers are generally not used. Or dynamic storage management is not necessarily used by default. Instead, you've got the programmer can create it using a pointer. But by default, everything is static. So it's in the static memory address, static areas of the process space. So it's not part of a feature of the pointer. doesn't actually need to be used for dynamic storage, so it's just used for an indirect addressing for the most part. I shouldn't say that though, but in C++, that's what would be for C. In C++, when I can go new object, well, that's dynamic storage management, so it is used for both in C++. So you don't have to know what is supported in any language in particular. There is a difference in a lot of ways with the pointers between C and C++. You're not responsible for knowing how dynamic memory storage management or addressing works in any particular language, by the way. So number 5, should a language support pointer types, reference types, or both? Modern day languages, they actually support both. So you have a pointer, you have a reference, and sometimes for example, in Java, they really mean the same thing. Actually, in C++, they pretty much mean the same thing as well. So fundamentals of pointer operations. Obviously, the assignment is a fundamental operation. We can set a pointer variable to an address of some object. We assign it. We can send 2 pointers to equal 2 pointers. So assignment expressions are generally supported. References and dereferences, that's that age-old thing with that asterisk in C and C++. Obtaining a value of a memory address is then a memory cell in which the pointer variable is pointing to or is bound to. So we can reference it, and then we can use the ampersand to get the address of that particular cell. We dereference it to go to the memory cell to go pick up what's there. So C++, that dereferencing is specified by a prefix in the identifier. Well, the referencing and the dereferencing is that asterisk in C and C++. In Java, you just leave the asterisk out. There's no asterisk. You don't need the asterisk. Why don't you need an asterisk? Well, because they just figured, why put it in when the language itself can dynamically determine that you're doing a reference and a dereference, especially if all of your objects are dynamic, then there should be no need to specifically put in a dereference. Therefore, we don't need it. So in that particular case, you just leave the asterisk out. So you're using a pointer, but you're not necessarily doing anything with it. I mean, you don't have to specifically put an asterisk in there to explicitly use it. It's an implicit pointer. So as an example, here's an example in C++ where we have integer j and then we have integer pointer. So this is a regular variable, C static variable. This is a pointer variable with the reference symbol. J is equal to, will follow PTR. This is a dereference. So PTR pointer is pointing to 7080. If we dereference it, we follow it, and we get what's there, 206. What's 206? Well, that's J. J is this piece of number here. So the address of operator, the ampersand, produces the address of an operator. So hopefully you guys remember this from your C++ class. And then the problems with pointers, well, we got that dangling pointer. Well, it's easy to create a dangling pointer. So you have multiple references to the same piece of memory, and then you delete the memory through one of the references, and then you don't do anything with the other one, and you've created a dangling pointer. So dangling pointers are dangerous. A pointer that points to heap memory variable that has been deallocated. For creating one, there's 3 steps to it. If you want to create one, allocate a Heap-Dynamic variable and set a pointer to point to it. Create or set a second pointer to the value of the first pointer. So they're both 2 pointers to the same piece of memory. Deallocate it through one of them using the first pointer. And then the second pointer is still there, still pointing to the memory that the first one was decided to deallocate. So that's not good. That means a dangling pointer is a pointer that dangles, that basically points to garbage, something that's not there anymore. Here's some code for it. If you want to create and using delete x here actually does it, because y is pointing to this address and x is pointing to the same address, and I deleted it through x, and then y is still pointing to it. Some languages take the extra references that are deleting to the memory that got deleted and set it automatically to null. Java will set it to null. Objective-C will set it to null. C++ does not set it to null. And because it doesn't set it to null in C++, we have the concept of the dangling pointer. We do not have, and we cannot create a dangling pointer in Python, C++, or in Java, for that matter. Actually, neither one of those languages would allow a dangling pointer, or Objective-C for that matter. Also, you have to consider that Objective-C and Python, as well as Java, all three of those languages that don't have dangling pointer problems, they also don't have memory leaks either, because all three of those languages have their own garbage collection. And so if, let's say, for example, the opposite problem, which is coming up in a slide set next, where instead of creating a dangling pointer, where you have a pointer that is pointing to something that's been removed already, it's not there anymore, and so the pointer is really invalid, it should be set to null. So those three languages set it to null. C++ doesn't do anything with it. Programmer has to set it to null. The opposite scenario is that you move the pointer away from that piece of memory and nothing is pointing to that memory anymore. The memory is allocated, but there's no way of getting to it. That's a memory leak or a piece of garbage. So languages implement garbage collection to go out there and clean up that memory. So not all languages have problems with dangling pointers, nor do they have problems with memory leaks. So the lost heap-dynamic variable, that's the memory leak. So a heap-dynamic variable that is no longer referenced by any program is wasteful because it's out there, it's been allocated, the cells are marked as being used, but nobody's using them. It's a waste of memory because now the memory is marked as being used, but nobody's using them. And so it's not available to be used by anybody else. You do that to all the memory, eventually you're going to run out of memory. To create a lost heap-dynamic variable, or aka garbage, so which is really what you're creating, you have a pointer P1 is set to point to a newly created heap-dynamic variable, and then P1 is later set to go to another newly created dynamic variable. Well, the first one that it was pointing to is now a piece of garbage. So the process of losing heap memory variable is called a memory leak. So the memory leak happens when you run out of memory because you've allocated and allocated and allocated it, and you've not deallocated it, and the compiler thinks it's being used, but nobody's referencing it. It's just garbage. So C++ has a special kind of pointer or reference types, which is a constant pointers. They're implicitly dereferenced. So that's the pointer used for formal parameters and function definitions. The advantages are for both the pass-by reference and the pass-by value. So if you're familiar with pointers, maybe you're familiar with the concept, and this is showing you the reference here, where P is equal to stuff. And so that's what they're calling a reference type. So I can send P to a function. I don't have to worry about it. I'm passing it by a reference if I do that. Or I can send what P is actually pointing to, and that's going to be a value. So Java only has references. It doesn't have any static data. Everything's a reference, but there's no reference and there's no dereference symbols. So the syntax of the language is a little bit different from C++ in that you don't have to put the asterisks in there. But it's doing the same thing. It's 100% references. There's no pointer or arithmetic possible. You can only point at objects, which are all on the heap. So there's no way of pointing to non-objects. But why would you? Because Java is 100% object-oriented. So everything is an object. So there's really not a limitation. It's just that you're pointing to objects. You're not pointing to, I don't know, random variables or things. For example, if you're writing a C++ program, you can go integer I, and you can go pointer, asterisk P, and then say that P is equal to the address of I. You can't do that in Java. there's no address of operator and there's no asterisks, but that's not an object. I is a variable, C static variable. You can't do that in Java. You would not want to do that in Java. There's no need to do that. So no explicit deallocator, either garbage collection, is used for deallocating. So the deallocator in C++ is the deconstructor. And some people call it a destructor. I call it a deconstructor, whatever you want to call it. It's part of the C++ implementation. Not part of Java. We don't need it. There's a garbage collector that's used instead. And then you don't have to turn on the garbage collector. It's part of the JVM. So the language itself takes care of it for you. Which means there's cannot be any dangling references and there's no memory leaks. So, and dereferencing is always implicit. It's always done. The dereference is always done by the compiler. There's no need to set anything to null. It is set to null automatically by the compiler. So C++ does not do that, by the way. So, right. Implementation of pointers and reference types in most of the larger computers, well, they're single values stored in either 2 or 4-bit memory cells. Well, nowadays they're just stored as regular variables and they follow the same data types as what we normally have. Same thing true for Java, by the way. The reference or the pointer is using the same data type concepts. So we don't necessarily need to worry about the number of bytes that is occupying. Now, a couple words on data collection or garbage collection as we have it. There's couple popular approaches. Now, this is kind of interesting. Java uses a lazy collector. This is an eager collector. The next slide is going to have a lazy collector. Objective-C used reference counting, which was a eager one. So what you have to do is keep track of the memory that's no longer being used. So how are you going to do that? You can keep track of references to the memory, and that's called reference counting. So this is the reference counter here, where we have 1, 2, 3 pointers that are pointing to this piece of dynamic memory. So at the memory location itself, there's a plus plus or minus minus when these references are created. So the reference counter says here's 3. If this is 0, it means nobody's pointing to it. If nobody's pointing to it, this is garbage, we should throw it away. And so the garbage collector does nothing more than come by and sweep up memory that's no longer being used. And what does it do? It doesn't do anything. It just marks the memory as available. So somebody else can come in and use it. It doesn't even clean it out. Java doesn't even clean it out. It just leaves the garbage there. Whatever's there. So it's really a garbage collector. It's not really collecting any garbage. Instead, it's just coming through and marking cells as available. Yes, you can use this one. Yes, you can reuse that one. Nobody's using you right now. So each memory cell is associated with a counter. And this is the reference counter approach. They call it the eager approach. This is an Objective-C technique. I shouldn't say that. Actually, Swift and some of the newer version of Objective-C uses a lazy approach, not a reference counter anymore. You can turn off reference counting. But reference counting was considered more reliable because it immediately picked up when it went to 0, it triggered, oh, okay, mark this cell as open, which was an instant kind of release of the memory. But you have that increment and the decrement every time a reference is set to the cell through that reference counter variable. So when a pointer is disconnected from the cell, the counter is decremented by 1. When the reference reaches 0, it means the cell has become garbage. The cell is returned to the list of available space automatically, and it's done when the references go away. And then we have a thing called a lazy approach. Well, lazy approach waits. Okay, so this is what Java does. If the user never runs out of memory, it doesn't even have to invoke, which I think is pretty good. But it'll wait until all the cells have been allocated. And the garbage protector will then come in and the process will start by setting indicators on all the cells to indicate that they are garbage. So the sweeper, and they call it it's a lazy sweeper. It's kind of like a broom, like it comes through and it kind of just hits as many cells as possible. And it says, are you garbage? Are you garbage? Are you garbage? And just marks them. So then when we need them, we can quickly just grab the cells. So when every cell in the program is traced, All of the reachable cells are marked as not being garbage and they're kept, and all of the unreachable ones turn into garbage and then they can be collected. So if you're going to use a sweeper or a non-sweeper, there's a sweeper and then there's a non-sweeper approach to it, but generally speaking, they just call it lazy collection. It's the lazy approach. And it's lazy because we're waiting until we're going to run out of memory. And then when we run out of memory, we're going to go find some. How are we going to go find some? We're going to sweep through, or we're going to scan through the memory. Either look for a reference to see if anybody's referencing it, or look for look for the signs of there not being any reference. Or better yet, just look for the references we can find and keep those and then take one of the other ones. So it's not quite as accurate. It's not quite as fast. And it doesn't operate unless it really is needed, which makes it more efficient if you think about it. So that concludes the concepts of Chapter 6, which is what we needed to get through this week. And so next week, I'm going to wait till next week to start in with Chapter 7. You should read Chapter 6. I would read Chapter 6 all the way to the cover to cover. Eventually, I'm going to go over and tell you which sections you should focus on. But for right now, I would at least skim through most of them. Don't worry about the garbage collection towards the end, although you might find it fascinating. I'm not going to ever test you on the different garbage collector techniques. What you want to be familiar with is the concept of garbage collection and how it handles or deals with the concepts associated with pointers and memory allocation. Garbage collection solves the issues of memory leaks, and so we don't have to worry about over allocating and not releasing the memory or making it available to be used. So in any case, reference counting or sweeping or lazy is pretty much all you want to be familiar with. You don't necessarily need to know all the terminologies, just a basic understanding of what garbage collection is and why it's used would be appropriate for that. So I hope you've enjoyed the video for this week. That concludes Chapter 6, and we will stop at this point and pick up on Chapter 7 next time. And I hope you guys are all staying safe and healthy, and I will see you for another video soon. Take care.